Welcome to Center of Math's series on graph theory. Today we're going to talk a little bit about Hamiltonian graphs. So a Hamiltonian graph is a graph with a cycle such that the cycle hits every vertex in the graph once, and we're not repeating any edges, we're not repeating any vertices. So Hamiltonian graph is a graph with a cycle that contains all the vertices of a graph. And one simple theorem about Hamiltonian graphs is that if we have a graph of over P, so it has P vertices, and the degree of each vertex is greater than or equal to P over 2, then that graph has to be Hamiltonian. And so we can prove this theorem. So first, if P equals 3 and we have degree is greater than or equal to P over 2, which is 1.5, so the degree of each vertex is actually greater than or equal to 2, since we can have a fraction degree. And so if the degree is just 2, that's just the complete graph of 3 vertices, and clearly this is Hamiltonian. So now we're going to assume P is greater than or equal to 4, and what we're going to consider is the longest possible path in the graph. So the path is a sequence of vertices, we don't repeat any vertex, and we're assuming we have some finite graph, so we have some finite path, and there is a set of maximal paths. A set of paths that have no larger paths, no paths with more vertices than those paths. So we're going to take one of these paths. We're going to say it begins at V1, ends at Vk. So the first thing we're going to note, so if V1, it has an edge going to a vertex that is not on the path, we can create a larger path. So therefore, there can be no edge going to a vertex from V1 that is not on the path. So the path must have size of greater than or equal to P over 2, because V1 has degree P over 2. So the next thing we're going to note is there must be an edge going from Vk to a vertex and an edge going from V1 to a vertex, such that these two vertices are adjacent to each other. And we can show this by contradiction. So in our path, if we assume Vi, so V1 we know is connected to so many Vi's, and we assume for each Vi minus 1 does not have an edge going to the final vertex Vk. Therefore, the degree of Vk, we take out all these Vi minus 1s because they're P over 2 Vi is connected to V1. There must be at least P over 2 vertices, different vertices of Vk cannot be connected to. And so taking all the vertices on a graph, minus 1, because Vk cannot be connected, have an edge going to itself. So therefore, the degree of Vk is less than or equal to P minus 1 minus P over 2, which gives P over 2 minus 1. But we have a degree of Vk is greater than or equal to P over 2. And so these two contradict each other. And therefore, for some Vi minus 1 is an edge going from Vi minus 1 to Vk. And so if we draw this, we have some edge going from Vk to V, or in this case Vi, V1 to Vi plus 1. And now here we have a cycle. So we can go from Vk to Vi from V1 to Vi plus 1 back to Vk. And so now we have a cycle from our path. And so we want to prove now that this cycle in fact contains all the vertices in our graph. So if we take some W not in our cycle, note in our cycle we have V1. V1 is connected to P over greater than or equal to P over 2 vertices in our cycle. So we have at least P over 2 plus 1 vertices in our cycle. Now if we assume W does not have an edge going to some vertex in the cycle, then the degree of W has to be less than or equal to P over 2 minus 1 minus P over 2, again, which is P over 2 minus 1. So once again, the degree of W will be less than p over 2 if it does not have an edge going to the cycle. Therefore, it must have an edge going to the cycle if this w exists. If this w exists, then using this edge to the cycle, it's easy to construct a path larger than the largest path we started with. You just go from W to the member it's attached to, and then go around the cycle and just end one before the last member. And then you have a larger path, which is a contradiction since we assumed we picked the largest possible path. And so therefore the cycle contains all vertices, and this graph is Hamiltonian. So quickly, a tetrahedron is a Hamiltonian graph that's not Eulerian. And this graph here, if two triangles connected at a point, it's an example of an Eulerian graph that's not Hamiltonian. This one's Eulerian because every vertex has an even degree. This one is not because this is not the case. This one's not Hamiltonian since you start at any side. You go one side, you can't come back to that side. You start at the middle point, you go one side, you can't go the other side, so it's clearly not Hamiltonian. This graph, it's easy to find a Hamiltonian cycle in a tetrahedron. So Eulerian and Hamiltonian graphs, neither set contains the other. So a well-known problem, the traveling salesman problem. If you have a graph with edges that are weighted, so they're assigned numbers, you want to try to find the shortest possible Hamiltonian cycle in the graph. So you visit each vertex once, and when you add up all the values of the edges, you get the minimum possible value from all these possible different Hamiltonian cycles in the graph. And so this is kind of like the problem you might encounter if you're a salesman trying to visit each city. Between each city, you have so much distance to travel. You want to visit each city once and return back, traveling the least amount of distance. Thanks for watching. Please check out salesmanmath.org, check out our blog, and follow us on Facebook and Twitter. Thank you.